Happy Pi Day, everybody. You know, the internet has made it easier than ever for people with obsessive personalities to come together to discuss the topic of their fixation. On the other hand, it has also made it easier for so-called regular people to observe these obsessive groups and regard them as lunatics, to pity and ridicule them. Just on YouTube, you can find 8-hour-long retrospectives of Nickelodeon teen sitcoms, 9-hour-long documentaries on Mario Maker troll levels, and even the Math Sorcerer's toilet paper playlist. I myself am not immune to engaging in such absurd projects. Just last year for Pi Day, I sat down and wrapped an absurd 17,000 digits of pi in a failed attempt at wrapping 20,000 digits. Many folks will observe these peculiar endeavors of their fellow man and think, what a waste. Imagine what meaningful things could have been accomplished with the time that these nerds have vanquished. But us nerds who crush the sands of time beneath our passions live in the darkness, engulfed by the shadow and the indomitable spirit of William Shanks. You see, it wasn't until 1961 that the first electronic desktop calculator emerged. But William Shanks was around 100 years before this, and he was fixated on pi and other mathematical constants, just as people of today are fixated on teen sitcoms and Mario Maker troll levels. And indeed, the lack of an electronic calculator was no obstacle to William Shanks, who in 1853 published what he called the rectification of the circle to 607 places of decimals. In this work, he showed his calculation of pi to 607 digits. And never content to leave the matter alone, in 1873, he published an approximation of pi to 707 digits. Again, this is well before the electronic calculator. These calculations were done by hand over hundreds of hours of labor and years of intense effort. For the uninitiated, it's probably worth addressing what makes pi so special. Why are we celebrating today? And why would anybody put forth such an extreme effort to calculating this number's digits? Most of you probably don't need much convincing that pi is special and worth celebrating, so let me try to keep this short. No matter the size of a circle, if you take the distance around it, which is called its circumference, and divide that by its diameter, which is the distance across the circle, you will always get the same number, being the famous and beloved pi. So the first reason pi is so special is that it's the unique ratio between the two most important measures of one of the most important shapes. As pi was originally discovered from circles, and looking at this ratio, it's no surprise that it comes up when circles are involved. But another thing that makes pi special is how frequently it comes up when you wouldn't expect it. One of the most famous problems from math history was to evaluate the sum of the reciprocals of the square numbers. 1 over 1 squared, plus 1 over 2 squared, plus 1 over 3 squared, and so on forever. Does this sum of infinitely many numbers get infinitely large, or does it approach a particular value? Certainly, this was a problem that only a first-rate mathematician would be able to solve. And sure enough, the legendary mathematician Leonard Euler showed in 1734 that it was equal to pi squared divided by 6. No circles involved, yet there pi is again. Another bizarre instance of pi appearing concerns this function called the Gaussian function, f of x equals e to the negative x squared. E is another famous number sharing many of pi's peculiarities, but we'll leave it at that for now. If you graph this function in the xy plane, it looks something like this. Ignore my first two failed sketches. One may ask what the area is underneath this famous function. Oddly enough, the area, which can be evaluated as what's called an improper integral, the area is equal to the square root of pi. Showing up in lots of interesting places isn't sufficient though. I mean, the number 2 shows up in lots of interesting places. It's not as widely celebrated as pi is. What else pi has going for it, which so often makes it an object of fascination, is that it's irrational. This means that pi can't be written as the ratio of any 2 integers. A result of this is that pi's decimal expansion continues infinitely. It never terminates, and it never settles into a repeating pattern. Without this property, we'd have no need for a legend like William Shanks calculating hundreds of decimal places of pi. And the other thing that makes pi particularly interesting for mathematicians is that pi is transcendental. This means that pi isn't the root of any integer polynomial. For contrast, consider the number square root of 2. The square root of 2 is also irrational, but it's not transcendental. That's because the square root of 2 is a root of an integer polynomial. In particular, x squared minus 2 equals 0 has root 2 as a root, meaning if we let x equal root 2, this equation is true. A consequence of this is that if we want to compute pi, it's going to take some clever techniques. Early approximations of pi, which were often good enough, are numbers like 25/8, 22/7, or even simply 3. But then, how did the humble Englishman William Shanks, born 1812 in the parish of Coronside, manage to calculate hundreds and hundreds of digits of this mysterious number? To explain his method, it will require just a little bit of trigonometry. This is a circle centered at the origin of the xy plane, and here is a radius of the circle. Starting from the end of this radius, I could draw a perpendicular line segment with whatever length I like. If I then take that perpendicular line segment and connect it back to the origin, we get a triangle, and perhaps more importantly, a central angle of the circle. Let's say we call this angle at the center of the circle theta. Let's say the radius is a, and the length of this vertical segment is b. Then there is a lovely trigonometric function called the arctangent function that relates these quantities. The arctangent of the side opposite the angle, which is b, divided by the side adjacent to the angle, which is a, so b over a. The arctangent of that is equal to the angle. This function is the inverse of the more well-known tangent function, but this one is more important for our purposes. Now, in this triangle, what happens when the angle here is 45 degrees? Well, if you remember your geometry, since this is a right angle, if this is 45 degrees, then this other angle is also 45 degrees, because in total the angles have to add up to 180. This means that when that angle is equal to 45 degrees, B is equal to A. We have an isosceles right triangle. Because if this angle is 45 and this angle is 45, then those sides opposite those equal angles have to be equal themselves. Beginners in geometry will usually use degrees to measure their angles, but once you get to trigonometry, calculus, and beyond, you'll often use an angle measure called radians. And in the interest of time, I'll just tell you that 45 degrees is the same as pi over 4 radians. This means that arctan of b over a, when b and a are equal, that would be arctan of 1, because b over a would be 1, and that will be equal to 45 degrees, which is pi over 4 radians. Long story short, arctan of 1, because b over a is equal in this case, arctan of 1 is equal to pi over 4. Then our mission is clear. We just need a way to calculate arctangent of 1, and then we can multiply that by 4 to get approximations for pi. And we're in luck, because as long as x is between -1 and +1, arctan of x is equal to this simple infinite series. This is just the alternating sum, so positive, negative, of odd powers of x divided by those odd powers. Of course, we want to plug in x equals 1, which is within the allowed bounds. Just plug 1 into this, and we're going to get pi over 4 to our desired level of accuracy. We just have to add up more terms to get more accuracy. This particular series is sometimes called the Madava-Gregory series. More generally, this is one instance of a Taylor series. And when we plug in x equals 1 to get this simple alternating sum of reciprocals of odd numbers, this is what's sometimes called Leibniz formula. So what do? Just 1 minus a third plus a fifth minus a seventh as far as we like to get a good approximation, multiply that by 4, and that's an approximation for pi. Unfortunately, there's one big problem, and that's the fact that although this series does converge to arctan of 1, it will get closer and closer as we add more terms. It converges very, very slowly. In fact, if we want pi accurate to 4 decimal places, or 4 digits after the decimal point, we need to add up 5,000 terms of this series. Even more absurd, for a modest 10 correct digits after the decimal point, we would need to add up a staggering 5 billion terms of this alternating series. So it's not like, yeah, it converges slowly, but if you really put your mind to it, you could get a great approximation for pi. No, these numbers are simply impossible. This is not gonna work. Interestingly, there are actually methods for accelerating the convergence of a series that could be used in this case. One of them is even called the Shanks transformation, although it's related to a different Shanks. However, none of those methods were known during our beloved William Shanks' time. No, our beloved William Shanks had to use a different tool, dating back to 1706. It was in that year that English mathematician John Machin published what would be known as Machin's formula. Well, we previously saw this equation wasn't super useful because the series for arctan 1 converges so slowly. The series for arctan of smaller numbers converges quite a lot faster. And so, the brilliant thing about Machin's formula is that it gives us a similar equation for pi over 4 using the arctangent function, but in this formula, the arguments of the arctangent function are much closer to 0, 1/5 and 1/239th. Those of you with prior knowledge of trigonometry were probably totally comfortable with this equation, but you may be wanting to be convinced of this one. In the interest of time, I'm not going to go through it step by step now, but I did go through it step by step in the past, and you can glance at that work here. It's all based on this arctangent identity. Down here, we find that arctangent of 120 over 119 is equal to this sum, but then we can replace arctan of 120 over 119 with this, and then we can replace arctan of 5 over 12 with this. We thus end up with 2 times arctan of 1/5, or 4 times arctan of 1/5, and then minus arctan of 1 over 239 because we subtract that from both sides, which just leaves arctan of 1 all by itself on the other side, and we know arctan of 1 is pi over 4. So then the task is simple. All William Shanks had to do was use this infinite series for arctan x, evaluate arctan of 1/5 to the desired level of precision, multiply it by 4, evaluate arctan of 1 over 239, subtract it, and then multiply that by 4 to get an approximation for pi. However, just describing it doesn't come close to conveying the organizational nightmare that this calculation would have been. To give you a better sense of the effort involved, let's just try using this method to calculate pi accurately to, let's say, 4 digits after the decimal point. The more terms of the series we use, the more accurate our approximation will be. To get pi correct to 4 digits, we're going to need 3 terms of the series. So then let's begin with our calculation of arctan of 1/5, and then we'll multiply that by 4. Again, we're going to approximate arctan of 1/5 using the first 3 terms of the series. The first term is just x, the input, which is 1/5. Then we have to subtract the input cubed divided by 3. 1/5 cubed is 1 over 125. Divided by 3 is 1 over 375. For the third term, we have to add the input to the power of 5 divided by 5. 1 over 5 to the power of 5 divided by 5 is 1 over 15,625. Just calculating the terms of the sum is difficult enough and would quickly require long multiplication algorithms done out by hand. Since we're only using 3 terms from the sum, I shouldn't put equals here, I should put squiggles for approximately. And you probably know that 1/5 is 0.2, but for these other 2 terms, you'd have to bust out long division to get a decimal approximation. I'll spare you the details of that effort. 1 over 375 is about 0.00267, and 1 over 15,625 is about 0.00006. We're going to go to 5 decimal places with this calculation. And if you do this arithmetic correctly, you'll arrive at an answer of 0.19739. We are kind of almost halfway done. Now we have to get our approximation for 4 times this. That means we have to take this guy and multiply it by 4. So our approximation for 4 times arctan of 1/5 is going to be 4 multiplied by 0.19739. And after putting in the effort to calculate this, you'll get an answer of 0.78956. So we've just completed this part of the formula, 4 times arctan of 1/5, for just 3 terms of the series, whereas William Shanks used hundreds of terms. And just in this calculation, of course, I've left out much of the effort that would have been expended in crunching these numbers. We would then have to proceed with an approximation of arctan of 1 over 239. Again, we would use 3 terms of our series. The first term of the series is just x, the input, 1 over 239. And for our fairly imprecise approximation, the other 2 terms, which would involve 1 over 239 cubed and to the power of 5, those other 2 terms will be negligibly small for our purposes. So we could stop here, where we would then have to do long division to get a decimal approximation of this fraction. We would find it's about 0.00418. Again, this is a headache, and I'm leaving out most of the work. Now, using John Machin's formula, we approximate pi by taking 4 times arctan of 1/5, subtracting arctan of 1 over 239, and then multiply that by 4 to get pi by itself. We thus have that pi is about 4 multiplied by 0.78956 minus 0.00418. Once again, there is number crunching to do here, but if you crunch the numbers correctly, you'll arrive at an approximation of 3.14152. We carried our computations up through 5 decimal places this whole time, and we got pi accurate to 4 digits after the decimal point by using 3 terms of the arctan series. You're probably thinking, wow, that's a lot of effort, especially considering the number crunching I left out just to get pi accurate to 4 decimal places. But William Shanks is an absolute monster. We just did 3 terms of the series and computed everything to 5 decimal places. William Shanks did those computations with 506 terms of the series, each one of them to 709 decimal places. Keep in mind, because of the nature of the series, half of the terms would be positive and half would be negative. This means that just in bringing together the positive terms for, say, arctan of 1/5, William Shanks was dealing with 253 terms, each to 709 decimal places, for a massive total of 179,377 digits just in bringing together the positive terms of a series for one of the arctan functions. The mere thought of keeping such a massive calculation organized boggles the mind. One can only imagine a massive scroll covered top to bottom in carefully written digits filling out an entire Victorian Victorian-era house. You may wonder how a computational feat of this scale could be possible without making any errors. The answer is that it's not possible. Indeed, the 707 decimal places of pi that William Shanks calculated were not all correct. It was a record. It was correct to a staggering 527 decimal places, so it's just as outrageous however you slice it, but they weren't all correct. And that was shown sometime around 1946. Records seem to disagree on the exact time, but it was shown by a fella named D.F. Ferguson. With the aid of a desktop calculator and this new formula for pi over 4, Ferguson calculated pi accurately to 808 decimal places. I have to imagine if he was shocked by how long his calculations agreed with William Shanks, but it was at the 528th place where a disagreement and indeed an error was finally found. The error here, of course, invalidated the rest of the digits in Shanks' calculation, and I'll leave links in the description if you want to see some more in-depth analyses of his errors. One would be forgiven for thinking that William Shanks' errors after the 527th decimal place went without any consequence. I mean, nobody actually needs to use pi to that many digits. However, there was a museum in Paris, which in the year 1937, in Hall 31 of the building, they had what was called the Pi Room, a circular room with 707 digits of pi in large wooden numerals going around the ceiling. 707 digits, of course, because it was thought that many digits of pi were known at the time thanks to the legend William Shanks. And I think the digits of pi were more important to nobody than William Shanks, so he would be very happy that they corrected their digits in 1949, shortly after the errors were discovered. Perhaps due to the errors in his calculation, it's easy to see William Shanks as a tragic figure. He seems obsessively committed to something, as if oblivious to the fact that most would regard it as totally useless. Just the thought of the intense arithmetic this man must have suffered through would be enough to give many school children nightmares. But this is what the man loved, and he was not at all oblivious to how useless it might seem. Indeed, in the preface to his 1853 volume, which gave pi to 607 decimal places, he says, in regards to his endeavor, he was fully aware, at that time, that the accomplishment of his purpose would add little or nothing to his fame as a mathematician, though it might as a computer, nor would it be productive of anything in the shape of pecuniary recompense at all adequate to the labor of such lengthy computations. He was anxious to fill up scanty intervals of leisure with the achievement of something original, and which, at the same time, should not subject him either to great tension of thought or to consult books. And so, in his calculations, he reveled, and in his shadow, we quake. Happy Pi Day.